Hi, I'm Bill Vales. Today I'm with Tom Vales, also known as Dr. Electricity. In our previous show on Fun with Science, in Radioactivity #1, we introduced the topic of radioactivity and discussed some of the basic principles and characteristics of radioactivity. Today we're going to build on these concepts. We are also going to discuss some of the ways radioactivity is used today and has been used in the past. Tom, welcome back.
Oh, long trip.
Okay. So in the first show, you did a nice job talking about the various particles, the alpha, beta, gamma particles, and how they're emitted. And we were doing experiments where you measured those using this device, which is a Geiger counter.
Yep, that's right.
Why don't you take over from here and talk about the Geiger counter?
Okay, well, we talked about radioactive elements giving off particles, and the particles were picked up by this device here, the Geiger counter. Well, when these elements are decaying, what they are trying to do is go back to a more stable state, either a non-radioactive element or lead. The thing is that not all of them get there at the same time. Some take a little, some take a lot of time. We're going to be addressing those.
Okay.
Now,
by a stable state, you're referring to the number of protons, should equal the number of...
Well, yes, because it's a non-radioactive state.
Electrons.
Yeah.
Okay.
So how do we measure the intensity and the longevity of radioactive elements? These are two things you really would like to know. The intensity basically is how hot is the element? How much radiation is it putting out? Obviously, a lot of radiation, it's all relative, okay? Too much or any radiation at all is too much. And then, longevity, how do we measure that? How long are these things going to be with us? So first, this little device here is called a Geiger counter, and it has a wand with the sensing tube on the end, and this is the body. This one happens to be made by Bicron. There are a number of manufacturers of these. And this one here is marked off on the dial in counts per minute. And that will give you a good idea of how nasty the thing you're measuring is. The most important part of a Geiger counter is the tube that is inside the counter. It is a thin wall tube. Sometimes parts of it will be made out of mica because you don't want to do anything to shield the tube from the radiation you're measuring. You won't get an accurate count. And it has a conductive outer shell, and it has a wire that runs right through the center.
Okay.
Those two are hooked up to the circuitry inside the Geiger counter.
Okay.
The last trick is they fill it with a semi-secret gas mixture. And the way it works, it's quite...
Why is it semi-secret?
Well, I think it's proprietary to some people. You know,
Do all Geiger counters use the same?
Not sure.
Okay.
When a radioactive particle, doesn't matter if it's alpha, beta, or gamma, comes through the wall of the Geiger counter, it causes an ion to form, When it hits a particle of gas, it knocks an electron off and becomes an ion. And basically what happens is, it's called an avalanche effect, it will just keep doing that until it gets to the center wire, conducts, feeds it back here, and it reads out in counts per minute.
Now, when you say it knocks an electron off, it knocks the electron off of an element.
Yeah.
Okay. So we have the protons.
It could be also a molecule,
Okay.
but it still would be an element. But
Okay. And the electron.
yeah, it just hits it,
And so that's actually coming off the element.
yeah.
Okay. Okay. And that's what this is measuring.
What that is measuring is the number of times a second that happens.
Okay. All right.
And it's the Geiger tube, as it's called. That's been in use for a long, long time.
Like 50 years, 100 years?
Well, no, I don't know about 100. Let's see, where are we? 2015? 1915? No, I don't think it'd be 100 years. I think
Okay.
it might be later.
Okay.
Now, this device has its limits. Okay? This will not show you something at a long distance. Okay? Now, if you're prospecting for uranium, you want to get a sense of where a radioactive field, if you want to call it, is coming from, okay? And if you use this is basically up close and personal.
Yep.
All right? You have to be on top of it.
Yep.
So the other type of detector that we use is called a scintillator.
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 Scintillation is a flash of light. And this gets plugged into the Geiger counter. And you can see it's a little bit different end on the tube. This type of device is very, very sensitive. In fact, you know, close up to anything on this table here would like overpower it. This is designed to find very, very weak radioactive signatures.
I see.
Hence prospecting for a mine.
I see.
Like, you know, get you in the general direction, and then when you get close enough, you'd have to stop using this and start using that.
Yeah.
But the way a scintillator works, and this will try to make this as simple as possible. It take a crystal, for example, of sodium iodide, and they take that crystal and they put it on the end of a special tube called a photomultiplier tube. Then they wrap everything in black tape and put it in a light-tight enclosure. So what happens is this. The crystal has a particular property, and that is when a radioactive particle hits it,
Okay.
it scintillates. It puts out a brief flash of light.
Okay.
The photomultiplier tube, if you look at those two words, photo and multiplier,
Right.
the flash of light comes into the tube and gets amplified,
I see.
hence photomultiplier.
Yep.
But it's very, very sensitive and not for use with this type of stuff.
I see. Now, when we were talking about the various topics for this show, I ran across some maps of that the government does of flyovers. They were maps of the United States or each state. And they sort of showed almost like a heat signature map, but it's a radiation signature map, where apparently from very high distances, you can detect the signatures. What sort of technology is used?
They have some incredible machines that can do stuff, you know, that's awesome. But yeah, you can fly overhead and get a radiation signature.
Yeah, I mean, there's maps available on the web that, you know, look up radiation map of Massachusetts, and you'll get a nice map of the various signatures of various radioactivity.
Yep.
And I can see that being useful for finding mines,
Yep.
understanding geologic deposits, for monitoring weapons programs,
Finding stolen
finding
nuclear stuff.
stolen material,
Yeah.
a lot of a lot of benefits to
Yep.
that. Okay.
Well,
So-
we've discussed
Okay.
the intensity with the Geiger counter, but we have another thing to talk about, the longevity. And the concept that came up for figuring this out is really quite simple. It's called half-life. And what they say is this: if you have a nuclear or radioactive element today, okay, just say for the sake of argument, you have 20 billion nuclei in this thing,
Okay.
okay? You go down the road, say, 50 years, and you find you've only got 10 billion nuclei. You have taken half, decayed them out, and that length of time between when you started and when you measured is what's called the half-life.
Okay.
Now, some things have,
Okay.
half-lives really have vary quite a bit. Uranium-238 has a 4.5 billion year half-life.
4.5
Billion
year
years, which means
half-life.
it's not going anywhere.
Yeah, fairly long.
But it also means that it is not radiating intense radiation for that. U-235 is 700 million years, okay?
Closer.
But then you get into things like, well, cobalt-60 is 5 years,
Okay.
all right? So that is more active than either of the uraniums.
Okay. More active, meaning it's emitting
Yep.
more particles
right.
to reduce in half
Yeah,
in
right.
5 years period of time versus the uranium in
Yep.
4.5 billion years.
Iodine-131, 8
Okay,
days.
come closer.
8 days, it's its half-life. And that is, again, a more active element
Okay.
than U-238. So it's just a way of gauging the activity of an element. If you have a very, very short half-life, the stuff is so hot,
Yeah.
is radiating so intensely that you don't want to even get anywhere near it.
Yeah.
And uranium, well, here in New England, in the pegmatite and
Yeah.
other rocks, there's plenty of uranium and there's radium,
Yeah.
but it's not just coming out, you know, in droves. It's just very, 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 you know, low. And the only time that people worry about it is if they have a high radon concentration in their house,
Yes.
because
yeah.
it's coming in from the rocks filtering through the foundation.
Right. We have a lot of granite in this part of the country, and granite has radioactive elements in
Yep.
it, and they decay.
Yep.
And along that decay chain is radon. And of course, in a house, you're concerned with it being enclosed.
Yeah.
Okay, so if there's not a lot of airflow, the concern is that you're trapping radon.
Yep.
Okay.
Yep.
All right.
Well, I'm going to give you a little bit here. We're going to talk a little bit about Madam Curie, who discovered radium and another element, polonium, that she named for her native country, Poland.
She was from Poland.
Yeah,
Yeah.
and she won 2 Nobel Prizes, one in chemistry, one in physics.
Yep.
And her husband, their life's work was isolating radium, and they had to go through tons of uranium ore, reduce it down, whatever. They worked basically in a shack. I mean, it had
Yeah.
bad lighting, bad ventilation,
Yeah.
stuff's boiling all the time, and they're in there every day of the week. But she did, you know, discover radium, and she also...
And at that point, they don't really know what they're dealing with.
Oh, no
Okay.
idea, no idea.
So there weren't a lot of protections, you know, as they're boiling or doing whatever they're doing to this.
Yep, that's right.
I've seen it referred to as pitch blend.
Yeah,
They're not aware of what they're inhaling,
No.
getting on their skin?
No, nothing.
Nothing. Okay.
Sometimes when scientists get driven like that, they kind of forget. I mean, they get caught up in the moment. They forget about the dangers, and just go blindly ahead. They had to boil this stuff down and reduce it, and I mean, they went through tons of uranium ore to get a very, very small amount of pure radium, which pure radium glows with a bright white blue light.
Okay. So she won 2 Nobel Prizes.
Right.
Her husband, did he win a Nobel Prize, or did she share a Nobel Prize?
I don't know if she shared one.
But her son also won a Nobel Prize.
There were 5 Nobel Prizes in the family.
Not too bad.
In fact, she had to go to what they called an underground college because the climate about women scientists and researchers was laughable at the time.
Yeah.
And people wouldn't teach them. They wouldn't, This woman had the drive of,
And didn't they also name an element after her?
No, they named a unit of measure after her.
Which is
the Curie.
The Curie.
The Curie.
Okay, all right.
Yep, and she coined the term radioactivity, by the way.
Okay.
Well,
okay.
This was quite an accomplishment, and the minute radium hit the market, so to speak, everybody wanted it. It was billed as the ray of life, the rejuvenating.
Like the internet. Let's get on it.
This is great. So scientists, doctors, hospitals, manufacturers, everybody wanted this stuff. And unfortunately, it also wound up in the hands of shysters.
Okay. But people didn't really understand everything that we understand today about the dangers of it.
That they were about to find out. So radium got to be used in a lot of things.
Okay.
I have samples here
Okay.
of
You have a lot of
some
stuff here.
items that you would find in use back in the 1930s, that contained radium, because everybody wanted to get on the bandwagon. And these things were still being produced, in some cases, up to the 60s before people found out. So we'll just go over a few here.
Now this is different than, let me just shut that off just for a second.
Yeah.
This is, I mean, you've demoed things like smoke detectors with americium in them, and those are still used today.
Yeah.
Okay, so that's at a safe level.
Right.
Okay, that's at a safe level. So these are things that they've learned was not at a safe level.
Okay.
Okay.
These are hands for pocket watches.
Okay, hold them out.
That's pretty. Again, that's an alpha. That's an alpha emitter.
Okay, so those are watch hands.
Yep.
You know, I think we all had a watch that glowed in the dark, and they glowed because of radium.
Yes, the thing, it was a mixture of radium salt, like radium chloride or radium bromide, with zinc sulfide. And when the radium would release an alpha particle, it would run into a zinc sulfide particle and cause a flash of light. Now, that's, all right, here's an item from the...
I'm going to put on my gloves after the fact.
This is called a lamp pull. It's a glass tube that has a coating in it, and it would be, you could snap this on the end of a pull chain for a lamp, and you could see...
Ornamental?
Well, functional.
Yeah.
I mean, it could... That was radium. Everybody had to get in. This is a compass for the U.S. Army. Uncle Sam never skimped on anything.
These are alpha emitters?
Yes.
Okay, okay.
Yeah.
Now, go back a second to the watch hands.
Yeah.
Where are those?
Right there.
Okay, right. Watch hand. How did the radium get on that watch hands?
Okay.
How did the radium get on the watch hands?
In the days when there were a lot of watches, pocket watches mostly, they were put on by dial houses. And what these places did was that they would get watch dials from a manufacturer and they would paint them. And,
Paint them?
Yeah, and typically the ones that the employees were young girls in their high teens, low 20s. And they were paid piecework, by the way. And they would paint the numerals on the watch dials.
So that's pretty fine work to have to
Yeah,
paint
it
that.
is. So they found it so they could do more and get, a better line. They take the brush and they tip the brush between their lips, okay? Just a little. And each time they did that, they ingested
radium.
a little bit of radium.
Wow.
And being kids, they'd paint their earlobes, their foreheads, their teeth with this stuff, go out on dates, and glow. And I mean, they didn't know. And it took a few years before the effects would start. And it was usually the same thing, that the girl would go to the dentist and she would complain of a toothache and he would pull a tooth and it wouldn't stop bleeding.
I see.
And some had tumors growing on their chins.
I see.
They all died.
Okay.
And they died a horrible death. Radiation poisoning is got to be the worst way to go.
So a lot was learned by that at the disadvantage of those women. That,
some was learned.
Painted the dials. Okay, what other things do you have?
This is something else here that would have been around the same time.
Which is about 1920?
Even before that, 1900.
1900, okay.
This is called a radium revocator, and these were made by a number of different concerns. Some made out of glass, but this is crockery.
Yeah.
And what this is what you would be. You buy this thing, you take it home, and it would tell you to fill it up with water.
Okay.
When you
So
go to
this
bed.
looks like a crock pot that you would buy.
it's just plain crockery.
A decorated, nice blue piece of pottery that you would buy.
Yep. Got a spout on the bottom. Some of them had
spigot.
Some had stands, some didn't. And
Okay.
the glaze contained the directions, which mainly said, fill at night before going to bed.
Fill with water.
Just with water.
Okay, fill it with water.
Then, upon arising, drink freely.
So,
Yeah,
So-
2, 4, 6, 8 glasses.
so you're putting water in this.
Yeah.
The water is taking on,
Oh, we haven't said that yet.
okay.
Here's the trick with this whole thing, is that the inside of this jug is lined with crushed uranium ore. And that's
Okay,
about 20,000 counts per minute.
okay.
And what is it doing? It is throwing radiation in, the radiation that's coming out of the uranium and radium.
Yeah,
You have some radon.
yeah,
Radon is a gas. It's a radioactive gas.
yes.
So the water would get full of radon. And as you're drinking it, you would be drinking the radon. Now, radon has I think it's about a week, maybe 5 or so days half-life.
Yeah, that sounds about right.
And somebody would say, well, that can't be that bad. Well, what did I say before about any radiation is too much radiation? Well, these people were ingesting a lot of radon.
Okay. So the state of thing, the state of this was people thought that this was making you healthier.
Yep, because that's what the people selling it told them.
Okay.
And in those days, you know, the attitude was...
But the government was well aware that these were being sold.
Oh, yeah, they didn't.
Okay, so...
They didn't really do anything about it.
Okay. Okay, so we have clock hands that were made fluorescent with radium. We have healthy water,
Yeah, good. Good, healthy.
in quotes, through a revigator.
Yeah.
Had a compass so we could find our way. Had a lamp pool so we could turn our
here's
lamps
something.
on.
Here's something else here.
Okay.
That, if you want to take a look at this, this is a probe from a violet ray machine, which is a quack medical device.
Okay, you showed that at one of our earlier Fun with Science
Yeah,
shows.
but not this one. This one has buttons in it, and
Okay.
the buttons have radioactive material.
right.
This way you can get the best of both worlds.
Oh, great.
You can
get ultraviolet
yeah, and
radioactivity. Great.
But you didn't have to have a certificate. You could buy any of this stuff.
Okay.
It really didn't matter. In
Okay.
fact,
Okay, what do you have here?
well, this is a piece of Fiesta ware. This was very big up until, well, in the 50s. And this particular color was called radioactive red.
I remember seeing this at flea markets.
Oh yeah, I got thrown out of a woman's flea market stall because I had my Geiger counter with me.
Wow.
But what the radioactive part of this, and here's another, although this isn't Fiesta ware. This is another piece that's...
Okay. Now, the radioactivity in here, these are clay products. Mm-hmm. Okay. Clay, feldspar.
Yeah.
So it's not that radium was applied to that material. Radium occurred in that material.
Well, yeah, but the radioactivity on these guys comes from the glaze.
From the glaze, okay.
And that's,
okay.
that's uranium oxide.
Okay. Okay.
But people, I remember, you know, relatives that had this stuff.
Sure.
People ate off it.
Yeah.
Nobody even thought about it.
Yeah.
You know, and then somewhere along the line we kind of woke up, I think it is.
Okay. Okay, so what else do we have here? What's this item here?
That is a telephone pole insulator.
Okay, let's talk about this.
It's basically
come over here
phone
and-
pole insulators
come
were
over here.
made by
we've-
the same companies that made pottery.
Okay, we've seen these on phone poles.
Yep.
Okay, let's see.
It turns out that whatever it was that they used in the glaze is radioactive.
Okay.
Now you're not, chances are you're not going to ever see or find a radioactive telephone pole insulator. This just, you know, one of those
Probably
things.
because you have them all.
Well, yeah, I have one. But I'll show you one other thing here.
Okay.
This is a tin of arium tablets. Okay, arium tablets, made by the Associated Radium Chemicals, Inc. There were 42 tablets in here.
Knowing what we know now.
Yeah.
Okay.
There's radium in these pills,
Okay.
and they would tell you
Okay.
to,
Now, do you have pills in here, or is
Yeah.
this just?
No, there are pills.
Okay, there are pills.
but I
in
won't
there.
open it.
Okay.
Take 2 tablets with glass of water before or after each meal. To derive the most beneficent effects, arium should be taken regularly. So you're basically poisoning yourself, okay?
Okay.
People were taking these things because we tend to assume a lot of things, and I mean, you know, you have a doctor and that. Why do you have a doctor? Well, I feel that the guy is good and he's not going to steer me wrong.
Mm-hmm.
Back in those days, when there was no watchdog agencies,
Mm-hmm.
people still had this idea that, oh, they're not going to do anything to me that's wrong.
State of the art at the
Yep.
time, and
Yep.
that's true with really any technology.
Yeah, no, that's
So-
true.
Okay, so what you've covered here on this segment is we've got a good sense of the Geiger counter, scintillator, and some devices that were used in the past.
Yeah, some. Yep.
Okay, some. There were certainly more. And that's probably a good place to break at this point. And on our next show, we should talk about where radioactivity appears in things that we use today.
Right, right. And also in minerals, which are actually today.
Okay,
And some of a lot of this is today.
Okay. okay.
Yeah, that works.
So we'll pick that up at our next show. So I hope you've enjoyed Radioactivity Part 2, and we'll look for you on Radioactivity Part 3. Thanks very much.